El día de hoy les va a hablar acerca de Cosmological Inflation and Symmetry Breaking. So, go ahead, Gianmassimo.
Okay, thank you very much. Thanks for giving me the opportunity to be here in Mexico and give a talk. So, my field of specialization is early universe cosmology and cosmological inflation. I know that this is an Institute of Astronomy, but what I will be talking about is mostly a connection between particle physics and the very first instance of our universe, that is cosmological inflation. So the main aim, just to be clear, the main aim of the talk that I will develop towards the end is to try to make a connection between cosmology, in particular early universe cosmology, and some aspects of particle physics, in particular aspects based on symmetry considerations. The concept of symmetry is very important in particle physics, and what I will try to argue is that the concept of symmetry can also be important for astronomy and for cosmology, for reasons that I will try to develop. So the main topic of my talk is what is called cosmological inflation. I think that everyone knows about at least this concept. What is cosmological inflation? It is a short period of extremely fast superluminal expansion of the universe that we think it occurred within the first second of our universe life. So there was a Big Bang, and then within the first second of our universe life, we believe that the universe expanded extremely rapidly, superluminally, for a very short period of time. And after inflation ends, normal cosmology begins, radiation domination, matter domination, the formation of the cosmological microwave background radiation, etc. But what I will focus today is exactly in the very, very, very first instant of our universe life, what is called cosmological inflation. So why do we believe that cosmological inflation occurred? Okay, inflation was proposed in 1980s, 1981 by Alan Guth in order to solve some of the basic problems, basic issues of standard Big Bang cosmology, what is called horizon, flatness, and entropy problems. I will just tell you with a couple of pictures why there is a problem with standard Big Bang cosmology. Okay, there is one problem that is called horizon problem. That is the fact that today we observed the large-scale structure of the universe. We observe the cosmological microwave background radiation. And what we see is that, for example, the CMB is extremely uniform in all regions of the sky. This is quite puzzling because if we think from the point of view of special relativity and general relativity, what we see is our past light cone. What we see is the cosmological microwave background radiation in our past light cone. Between the formation of the cosmological microwave background radiation and us, a lot of years passed, around 15 billions of years. But if we think to when the cosmological microwave background radiation was formed, it was formed only around 300,000 years after the Big Bang. What we see is a surface, a cosmological microwave background that is extremely uniform. But what happens is that different patches of this background were never in causal contact one with the other. But nevertheless, they are all similar. The puzzle is that we cannot explain why different regions of the sky that we see very uniform are such, since since they have never been in causal contact one with the other. A possible resolution of this kind of problem is to make the hypothesis that there was a period of extremely fast superluminal cosmological expansion in the very early seconds of our universe life. So what happens is that although signals cannot travel faster than light, we believe that during inflation, space-time itself expanded faster than light. This is not forbidden by special or general relativity, and this helps to solve what is called the horizon problem and actually all the problems of standard Big Bang cosmology. This was the reason that forced Alan Guth to propose this idea of superluminal, extremely fast expansion. But what is very interesting is that inflation doesn't only solve these kind of problems, it also provides the initial condition, a theory for the initial conditions of our universe. In particular, it provides a theory that explains the temperature anisotropies of the cosmological microwave background radiation. So I'm sure you heard about all the discoveries of WMAP and Planck satellites. What they did was to study the statistics of the small temperature or the small fluctuations in temperature of the cosmological microwave background radiation. Cosmological inflation is able to explain the statistical properties of temperature fluctuations, as I will review in few slides. So inflation not only solves these problems, it also provides an explanation of why the pattern of temperature fluctuations of the CMB is the one that we observed. Also, for what respects the formation of large-scale structure and galaxies at very large scales in our universe, inflation is also able to provide the seeds, the little seeds, from which the matter starts to collapse gravitationally and produce galaxies. So inflation provides what are called the initial conditions, the little seeds, from which then galaxies and all the matter, all the objects that we observe start to form. So inflation is a very interesting and powerful idea. So how does inflation explain, for example, the patterns of temperature fluctuations? So this is a very interesting story for a particle physicist, because what inflation does is actually to take, so what happens is that in the very early instance of our universe, there are quantum fluctuations. There is really quantum mechanics and quantum field theory that works. And what inflation does is to take the quantum fluctuations that are produced by some processes of very early universe physics and stretch them, and it makes them extremely large. Why so? Because I told you that inflation corresponds to an extremely fast period of expansion. What inflation does is essentially to take quantum fluctuations and expand them into very large cosmological scales. These quantum fluctuations that are expanded by this process of inflation then form the seeds for the galaxies and form the temperature fluctuations of the cosmological microwave background radiation. So you see, this idea is very nice because it solves the problems of standard Big Bang cosmology, and it produces a theory that for cosmological fluctuations and a theory for the distribution of irregularities in the CMB that can be tested. And indeed, starting from 1990s, there have been a lot of experiments to try to test this idea of inflation. How do you do this? By studying the cosmological microwave background radiation. Before going to that, so let me tell you what physicists think about inflation. Because you can ask, why our universe accelerated for a short period of time in the early stage of its life. Physicists believed that there was some form of energy density that was working in the first, during this period, that was producing this exponential, this superluminal exponential expansion. What is this energy density? It is what is called a scalar field that rolls over a potential. I think that you heard about what is a scalar field. It is a sort of, okay, for this talk we can think of it as a sort of energy density like radiation and matter, but with specific properties. And physicists try to invent models based on the dynamics of these scalar fields, of this kind of energy density, so that these models produce this kind of cosmological expansion, early universe expansion, which corresponds to inflation. So there are many, many models of scalar fields that are able to produce inflation, as I summarized in the previous slide. So here you see, okay, the idea is that inflation, we think that inflation was produced by this kind of special energy density, a scalar field, and then at a certain point inflation ends and normal cosmology starts. During inflation, it is very interesting because during inflation, our universe was extremely symmetric. It was a sort of space-time that is called de Sitter space, or better, quasi de Sitter space, that is an extremely symmetric space-time that is studied in general relativity by mathematicians, etc., because it has a lot of symmetries. It is a very particular, very easy and very, it is a rich, kind of space-time that is rich of structure. What is interesting is that in the very early universe, then, we believe that our universe was much more symmetric than what is today. It was a sort of de Sitter space. So in the past 20 and 30 years, there has been a lot of connection between cosmologists, early universe cosmologists that try to understand inflation, and particle physicists. Why? Because cosmologists needed a model, needed ideas to try to describe inflation. And particle physicists were very happy to try to provide theories to explain why inflation occurred and how inflation occurred. For example, you surely heard about the Higgs boson that was discovered in 2012 in Geneva, in Switzerland. Okay, it might be that this very same Higgs boson, that is a scalar field, can be the responsible for driving inflation. So among the many models of inflation, there are models that use this very same Higgs field, the Higgs scalar, to drive cosmic acceleration in the early universe. Or maybe you heard about string theory, grand unification theories. There are a lot of fundamental theories in particle physics that have a lot of scalar fields that can drive inflation. And so many physicists try to find models of inflation based on this kind of fundamental theories of particle physics. So there is a lot of interaction between physicists and cosmologists. But what is nice is that inflation can make predictions, very well-defined predictions, that can be tested with the cosmological observations, in particular with the distribution of temperature fluctuations in the CMB and with the distributions of galaxies in the sky. So what is the idea? Okay, always in an easy way, so as I was telling to you, we believe that there was this kind of energy density, scalar field, that was driving inflation. This kind of energy density is characterized by quantum fluctuations in its magnitude. These fluctuations of this scalar field, that is called the inflaton, get converted into metric fluctuations. Why? Because it is the idea of general relativity is that matter produces geometry. So the fluctuations in matter, in the scalar fields, deform the metric, deform the geometry of the space-time. After inflation ends, these deformations of the geometry get converted into deformations of the cosmological microwave background radiation. So we believe that the temperature anisotropies, the little temperature anisotropies that we see in the CMB are directly connected with the fluctuations in the energy density that produces inflation. All this is a nice story, and you can make predictions. You can make predictions for the statistics of temperature fluctuations. For example, for the 2-point functions between these red spots in the cosmological microwave background radiation. All the predictions of inflation are very well confirmed by data. So the data of the WMAP satellite or Planck satellite fit very well with the predictions of inflation. Actually, cosmologists, just for simplicity, instead of making predictions about the temperature anisotropies, the temperature fluctuations, make prediction about a quantity that is called zeta that is directly related with delta T over T, just for convenience. But you see, here there are data. This is the theoretical curve. So there is a very good agreement with observations. Actually, it is also possible to provide some numbers, not only plots. For example, it is possible to make predictions for the amplitude of the 2-point functions that is the statistics of the cosmological microwave background radiation. For the amplitude of the 2-point function in what is called in Fourier space, so you take the Fourier transform of the 2-point function, and for the scale dependence of this quantity. So how this 2-point function depends on k, that is the Fourier mode. It is possible to provide some numbers. Inflation makes predictions. Different models of inflation make similar predictions, and it is possible to really test these predictions with the observations, for example, the Planck satellite, that provide very precise measurements of these properties. So it is possible to really provide, it is precision cosmology, you can really provide precise measurements about the statistics of the temperature fluctuations. The inflation makes predictions that are very successfully confirmed. So far it is 30 years that people are really make precise measurements of cosmological microwave background radiation. So for the next years, there are very challenging problems for observers. Why so? Because inflation makes not only the predictions that I told to you about the statistics of the 2-point function, it makes also other predictions about about two things. One is what is called non-Gaussianity, and the second one is primordial gravitational waves. That nowadays is a topic that, as you know, is extremely interesting. So let me tell you a little bit about non-Gaussianity, and then I will tell you about what inflation says about gravitational waves. So what is non-Gaussianity? If you heard talks about of people from the Planck collaboration, so what was very important for them was to measure not only the statistics of 2-point functions, of temperature fluctuations of the CMB, but also higher order point functions, 3, 4, etc., what are called endpoint functions of the cosmological microwave background radiation. Why it is interesting? Because it can tell us a lot of information about the origin, about the fields, about the energy density that drives inflation. What are called interactions of the scalar field that was driving inflation. So we believe that there was a scalar field, but we don't know a lot about the details of the theory for this scalar field. Studying endpoint functions, so the statistics of 3, 4, etc., endpoint functions of temperature fluctuations or of theta, one can learn a lot about the details of the physics associated with inflation. Planck collaboration studied a lot this kind of endpoint functions, but so far no detection of has been made. It may be that the amplitude of these endpoint functions is too small to be observed. There is a lot of observational effort in order to detect this kind of properties. So this is one prediction. Inflation predicts them. We don't know the amplitude. And people are still looking for this observable that is called non-Gaussianity. Second thing are primordial gravitational waves. So inflation, this period of accelerated expansion, not only produces temperature fluctuations in the CMB, we believe, okay, the theory produces also gravitational waves. So we believe if inflation is correct, for sure there is a background of gravitational waves around. We don't know its amplitude, but we know that there is this kind of sea of gravitational waves that is produced by this period of inflation. The properties of this background of gravitational waves are very similar to the background of temperature fluctuations. So we expect that the statistics of the gravitational waves have properties that are very similar to the ones of the temperature fluctuations. So as you all know, early this year, the first example of gravitational waves have been directly detected by LIGO. This was an event associated with black hole mergers, but maybe also it will be possible to detect inflationary gravitational waves by that mean. So let me tell you what cosmologists are trying to do now in order to detect gravitational waves from inflation. So what happens is that the cosmological microwave background radiation, that is the early universe radiation that arrives up to now, it has not only temperature fluctuations, but it is also characterized by polarization. So the light that arrives to us is also polarized. And what cosmologists are exploiting is the fact they are trying to observe the polarization of the cosmological microwave background radiation. There are two kinds of polarizations, what are called E modes and B modes. Theoretically, we know very well how to describe this kind of polarization of the CMB. And we know that one of these modes that are called what correspond to the B modes can be only produced by the gravitational waves, by the primordial gravitational waves. So if we are able to see these B modes in the CMB, it will be for sure an indication that there are these gravitational waves produced by inflation. You heard a few years ago there was an announcement by BICEP that they were claiming to have seen these B modes, but then you know the story. It was not true. Today there are a lot of experiments that are trying to study the polarization of the CMB in order to find these B modes. So inflation makes certain predictions for the properties of the tensor fluctuations. I will not go through them, but let me just say that you can ask whether we can see primordial gravitational waves with the detectors like LIGO, or maybe you heard about LISA or ELISA. These are detectors, interferometers that will be built and sent into space in 10, 20 years. Unfortunately, okay, this plot shows the sensitivity of gravitational wave interferometers, that the ones that are planned, that are functioning today and that are planned for the future. So this is the sensitivity. So the gravitational wave interferometers can detect gravitational waves with amplitude that are above these lines. This is LIGO and advanced LIGO. This is LISA and DLISA. So the gravitational waves produced by inflation stay below these lines, at least the ones that is produced by the simplest models of inflation. This is why it is very difficult to detect gravitational waves that come from inflation with interferometers, because their amplitude is too small. But as I will try to show later, there are models of inflation that can change this picture. So you see, let me return 1 second. So there are two big challenges for observers for the next 10, 20, I don't know how many years. Non-Gaussianity and primordial gravitational waves. If we see them, so we will learn a lot about this very interesting epoch of our universe that was cosmological inflation. So there are also questions for cosmologists, for theoretical cosmologists like me. So there are some questions that are interesting to study. For example, I told you that there are many ways to produce inflation. There are many models based on scalar fields that can produce inflation. So the big question is how to distinguish among different models. There are models like Higgs, the Higgs particle, that can produce inflation. There are many other models. They give very similar predictions, and it is hard to find ways to distinguish among them. Also, another big worry that everyone has is that there are some predictions of inflation that cosmologists still didn't work out. Maybe there is some prediction of inflation about the statistics of the cosmological microwave background radiation that is realized by data, but people didn't still think about to look to data in a certain way such to reveal some properties of inflation. So there might be something to the data that we still don't know. The data are really a lot. So the question is to be sure that we really look at the data in the most exhaustive ways, in particular to the cosmological microwave background radiation. And then there are also possible problems with inflation. For example, maybe you heard that there are anomalies at very large scales in the CMB. The CMB is uniform, but there is what is called a power asymmetry in the power spectrum. That is, a region of the sky is slightly hotter than the other region. Inflation cannot explain this fact. Also, there are issues about the production of large-scale magnetic fields. Astrophysicists are observing very large-scale magnetic fields in the intergalactic medium, and we don't understand why they are there. Inflation could be a way to produce them, but we don't know, really. So if all these data are correct, then the simplest models of inflation cannot explain them. So something else should be developed. So you see, we are in a situation now in which there are big problems for observers, big problems for theorists, and this is why I think this kind of subject of very early universe cosmology is very interesting, because there is a lot of connection between particle physicists, about observers. So let me tell you in the last part of my talk about a new perspective to inflation that has been developed in the past 10 years. This new perspective asks us to think to inflation in a way that comes from particle physics. Maybe you heard about the standard model of particle physics. So what is nice about the recent approaches, the modern approaches to particle physics, is that people insist on symmetries. So in particle physics, what is very important is to specify the symmetry of a system. For example, for the standard model of particle physics, we know that it is very symmetric. It has a symmetry that is called SU3 cross SU2 cross U1. I don't want to enter into details of this. But what I want to say is that now cosmologists are trying to take the ideas that come from particle physics and try to apply them to understand the process of inflation. So the attitude, the new approach to inflation is what is called effective field theory of inflation. And this kind of word is taken from particle physics. The main idea is only the following, is to try to focus on the symmetries that were there in the very early universe, in the very first instance of our universe life. So, while so far people consider different models of inflation, models that come from particle physics, models that come from string theory, Higgs inflation, etc., the new attitude is to say, okay, let's not worry about the model. Let's just focus on the symmetries of the space-time during the inflationary era. This is a completely change of paradigm, and it is a very powerful way to think to inflation. And this is a very nice example for me to use more ideas that come from particle physics to cosmology, to try to explain the properties of the cosmological background radiation, etc. So let me tell you with some pictures, which is why it is very important to use symmetries for cosmology. So in one picture, let me tell you one story. This story is a theorem that is used every day in particle physics that is called Goldstone theorem. This Goldstone theorem says that if you have a symmetry and you break it, then you start to propagate a massless particle. Whenever you break a symmetry, actually technically a global symmetry, you start to give dynamics to a massless particle. Okay? So this is just an enunciation of a theorem. So for example, if you have a pencil in this table, and if a pencil is really vertical on this table, you have a rotational symmetry. But if the pencil is slightly deformed, you break the rotational symmetry. And you produce a potential that actually resembles a Mexican hat potential of the Higgs field, and you produce a particle. Okay? So the dynamics of this particle, that is called Goldstone boson, is completely determined by how you break this symmetry. Okay, good. This is something that particle physicists use every day. But we can ask then whether there is a symmetry that is broken in cosmology, during inflation. And actually, yes, there is one symmetry that is broken during inflation, and this symmetry is translation along time. So if we think to space-time as a space-time that is determined by time and by free spatial coordinates, in cosmology, we break what is called time reparametrization. Because if we proceed with time, we don't see the same universe, because at each time, the scale factor changes, and so the symmetry that is called time reparametrization is broken, just because cosmology defines what are called preferred time slice. During inflation, the energy density associated with the scalar field is breaking a particular symmetry that is called time reparametrization. Good? So what are the consequences of this? Is that in cosmology in general, and during inflation in particular, different slices of time are not the same. So the cosmological expansions defines what are called preferred time slices, and you break time translation symmetries. If you proceed with time, you see a different universe, because the universe expands, the scale factor changes, and so you break this symmetry. Good. So what is the consequence of this? Is that you produce a particle that is called the Goldstone boson that is associated with this broken symmetry. And actually, this Goldstone boson, you can work out the details of its dynamics. It produces what is called curvature perturbations and the CMB and the temperature fluctuations of the CMB. So what is this? So if with this kind of approach, with this kind of attitude that is very model independent, you can again understand the pattern of temperature fluctuations of the cosmological microwave background radiation. So you can return and study the statistics of the CMB without thinking to a particular model, to a Higgs field as driving inflation, etc. You can study in a very general way this kind of issue, and you can reproduce the same kind of predictions that were obtained before. But what is interesting is that now the predictions are not linked to a particular model, but they are linked only to this kind of general idea of symmetry breaking. So you have only to specify which are the symmetries that are broken by the cosmological expansion. So this is interesting because it is very powerful, it is model independent, and by this means you can really study completely and exhaustively all the predictions of models of cosmological inflation that break this kind of symmetry. So all the predictions tested so far are in agreement with this, in my opinion, very interesting approach based on symmetries to inflation. Now, you can also ask, okay, so far we know that cosmology breaks time translation because as time passes, the universe expands. So time translation is not a symmetry in cosmology, and in particular during inflation. You can also ask what happens if during inflation you break also what is called space reparameterization. These are what are called diffeomorphisms of general relativity, the symmetries of general relativity. You can ask whether it is possible to completely break all the symmetries of space-time during inflation. You can ask why I want to do so, because if you start to break also space reparameterization, you can break the statistical isotropy of the CMB, and you might be able to explain some of the anomalies that people see in the cosmological microwave background radiation, like what is called the power asymmetry that I was mentioning before. So the question is whether with this approach based on symmetry breaking, you can describe more in general models, scenarios for inflation that can explain more general observations. So the idea is that in this case, if you break what are called space reparameterization, you produce other Goldstone bosons besides the one that I mentioned before. And these Goldstone bosons are called phonons in analogy with condensed matter physics. So I don't want to go into details, but I just want to tell you that if you start to break all the symmetries, also space reparameterization during inflation, then you can change the predictions for the gravitational waves. You remember before I was telling to you the spectrum of gravity waves produced during inflation has an amplitude that is too small to be seen directly with interferometers. Maybe you can see it with B modes, but not with interferometers. Okay, if you instead start to break all symmetries during inflation, you change the predictions. There are models of inflation that can do this. You change the predictions and you can find scenarios, models of inflation, in which, okay, this line represents the spectrum of gravitational waves produced during inflation. And you see, and these instead are the lower bounds for detections from an interferometer that is called ELISA. If we are lucky, in 20 years, we might be able to see, directly detect with interferometers, gravity waves produced during inflation. Then in this kind of scenarios, let me just tell you in 1 second that you change completely the prediction for the other observable that I was mentioning before, that is primordial non-Gaussianity. You can produce kinds of non-Gaussianities that are very different from the standard models of inflation, and that might be there into the data, also in Planck data, and people are now looking for these kind of non-Gaussian signals to try to test and to probe this approach to inflation. So let me conclude. The main message was that, okay, inflation is very interesting. There is a new approach to study the predictions of inflation that is based on symmetry. It gives distinctive observational consequences. It is interesting from the theoretical point of view. And people is now really working hard to try to find observational distinctive waves to probe scenarios of inflation based on symmetry breaking. So let me end here.
This is a very innocent question, I am sure. You say that from inflation you can predict the shape of the distribution of fluctuations in the microwave background. On the other hand, our colleagues say that these fluctuations, this distribution, this function, these curves, allow us to calculate the amount of dark matter, dark energy, dark ages.
Dark matter, yes. not dark energy, but dark matter.
And normal matter, baryonic matter. So my question would be, these predictions from inflation include the proportions of these matters?
Yeah, of course, okay, inflation, during inflation there was not dark matter. It was produced after inflation. But the shape of the power spectra of the CMB that I shown here take into account the fact that the cosmological background was produced 300,000 years after the Big Bang. Then light took a lot of time and there was a long path between the production of CMB and today. And so this CMB is sensitive to what happened from its formation to today. And you have to take into account of dark matter. You have to take into account of dark energy. You have to take into account of many of the things that you said in order to produce this kind of curves and in order to compare with data. So all these kind of curves are done in a specific cosmological model that is called lambda CDM. So you have to take into account of all the universe evolution in order to do this kind of curves. Of course, what inflation gives to you is the initial condition. It is very powerful to give the initial condition with certain properties, certain statistics, and then you had to work out and include all the effects that you mentioned in order to go from the initial conditions to the cosmological, to the patterns of the CMB that we observe today. So the answer is yes, we have to take into account of everything. But what inflation does is to give you the initial conditions. And this is because otherwise there would be no way to explain why the initial conditions.
The fluctuations themselves, you mean?
Yeah,
the
the
temperature
initial
fluctuations.
fluctuations. The initial fluctuations with that statistics.
But certainly not the shape. My question is inflation reflected in the shape of this curve?
Yes, it is reflected.
It is?
Yes.
Shit, then I don't understand.
Yes. It is reflected.
Okay.
Yes.
I don't know if it's prediction or you are calculating the...
No, there is a prediction for what respect the distribution, the statistics of the initial fluctuations. Then you calculate all the rest. Then you, okay.
Other question?
Thank you. It's a comment. This is a topic very interesting and nice, Congress budget talk. And so when did you talk one prediction of this a model for fluctuations in the inflations, it's the gravitational waves.
Yes.
So it's interesting because the gravitational waves is the orange is about only merger of the higher density bodies, right? So you told these gravitational waves is produced by the
expansion of
by the expansion, but only by the different temperature gradients, temperature gradients. Is it correct?
Actually, yeah. What happens is that the very same expansion of our universe, the superluminal expansion of our universe during inflation, produces these gravitational waves. These are really quantum effects. It is quantum mechanics that produces these kind of gravity waves with a certain amplitude, and then they are stretched into cosmological scales by this kind of expansion. So it is a completely different pattern of production from black holes, from the black hole mergers that has been observed. But inflation makes the prediction that they should be there. I mean, if you believe to inflation, then you know that there is this background, and cosmologists are trying in all ways to detect them. We don't know the amplitude. That's the big question. It is challenging, but okay. It was challenging also to produce this kind of curves, and they have done it. I'm optimistic.
More questions, comments, suggestions? Okay, if there are no comments, suggestions, let's thank to Massimo, Gianmassimo, again.
Thanks.
All of you are invited to the after party outside. Thank you.
Sí, me dijeron. Perfecto, gracias. Gracias. Hola, mucho gusto. Sí, español.
Mira, en el tiempo de Planck, poco antes de la inflación, ¿no?
Sí.
Entonces, el universo se expande.
No, digamos, realmente la gente piensa más o menos en el tiempo de Planck.
Tiempo de Planck, ¿verdad?
Un poquito después, pero muy poco.
Todo el tejido espacio-tiempo se expande a una velocidad superlumínica exponencial, ¿no?
Esto es increíble, pero es lo que pasó.
De un átomo,
Sí.
tamaño, entonces queda oscilando en los bordes.
Sí. Es increíble, pero es lo que pasó.
¿Eso se puede estudiar en forma acústica?
No
oscilaciones
tengo idea.
acústicas,
No sé qué.
esto
Nunca
más
lo
avanzado,
escuché.
no, pero es que están las oscilaciones acústicas de variones.
Sí, 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 sí. Esta, sí. Vi yo. Sí, sí,
Las
sí, sí.
oscilaciones acústicas
Ya
de variones.
lo vieron, lo
Sí, sí.
misuraron, sí. Lo midieron, sí.
Esas oscilaciones se pueden estudiar en formas acústicas de variones, ¿no?
Sí, sí, porque lo observaron en vídeo asociado al CMB. Se puede es otra manera de confirmar la inflación. Es interesante. Lo bueno es que podría ser mucho peor. O sea, la matemáticas no es tan complicada.
No, ¿verdad?
Porque las fluctuaciones son todavía en un régimen lineal.
Lineal, un régimen lineal, exactamente.
Entonces no necesitas grandes